The Mysteries of Venus's Toxic Atmosphere. Introduction: Earth's Evil Twin. Venus, our closest planetary neighbor, presents one of the most extreme and mysterious environments in our solar system. Often called Earth's sister planet due to its similar size and mass, Venus is in reality more like an evil twin, a hellish world shrouded in thick clouds of sulfuric acid, with surface temperatures hot enough to melt, lead and atmospheric pressure equivalent to being 900 meters underwater on Earth. While Mars has captured much of the public imagination as a target for exploration and potential colonization, Venus remains a scientific enigma, its toxic atmosphere hiding secrets that challenge our understanding of planetary evolution and climate dynamics. The Venusian atmosphere is a monster of planetary science, a choking blanket of carbon dioxide 90 times thicker than Earth's atmosphere, laced with clouds of concentrated sulfuric acid droplets and churning with winds that race around the planet at speeds exceeding 350 kilometers per hour. Surface temperatures reach 465 degrees Celsius, maintained uniformly across the entire planet by the most extreme greenhouse effect known in our solar system. This is not merely an academic curiosity. Understanding Venus's atmospheric catastrophe may hold crucial lessons for Earth's own climate future. The mysteries of Venus's atmosphere extend far beyond its toxicity and extremity. Scientists grapple with fundamental questions. How did a planet so similar to Earth in size and distance from the Sun become such a radically different world? What caused Venus to experience such extreme greenhouse warming? Why does the atmosphere rotate 60 times faster than the planet itself? What chemical processes maintain the bizarre composition of the Venusian clouds? And perhaps most intriguingly, could life exist in the upper atmosphere of Venus, floating in the cloud layers where conditions are less hostile? This exploration of Venus's toxic atmosphere will delve into these mysteries, examining what we know, what puzzles remain, and what this alien environment can teach us about planetary science, climate physics, and the limits of habitability in our solar system and beyond. Venus, a profile of extremes. Venus orbits the Sun at an average distance of 108 million kilometers, compared to Earth's 150 million kilometers. This proximity to the Sun contributes to Venus's heat, but it cannot alone explain the planet's extreme temperatures. Mercury, which orbits even closer to the Sun, is actually cooler than Venus because it lacks a substantial atmosphere. Venus has a diameter of 12,104 kilometers, just 650 kilometers smaller than Earth, and a mass approximately 81% that of our planet. These similarities in size and composition have long led scientists to wonder why Venus evolved so differently from Earth. One of Venus's most peculiar characteristics is its rotation. The planet rotates on its axis extremely slowly, and in the opposite direction to most planets in the solar system, a phenomenon called retrograde rotation. A Venusian day, the time it takes for Venus to complete one rotation, lasts 243 Earth days, while a Venusian year, one orbit around the Sun, takes only 225 Earth days. This means that a day on Venus is actually longer than its year. Moreover, Venus rotates from east to west, so the Sun rises in the west and sets in the east if you could see the Sun through the dense cloud cover, which you cannot. The Venusian surface, revealed by radar mapping from spacecraft like NASA's Magellan mission, shows a volcanic world with thousands of volcanoes, vast lava plains, and relatively few impact craters, suggesting that the surface has been geologically resurfaced relatively recently in planetary history, perhaps within the last 500 million years. The surface is dominated by volcanic features, including enormous shield volcanoes, lava channels thousands of kilometers long, and unique geological structures called coronae, circular features, created by upwelling of hot material from the planet's interior. But it is the atmosphere that defines Venus and makes it one of the most hostile environments known. The Venusian atmosphere extends hundreds of kilometers above the surface, far higher than Earth's atmosphere, and its complex chemistry and dynamics continue to puzzle planetary scientists despite decades of study. Understanding this toxic envelope requires examining its composition, structure, dynamics, and evolution, and confronting mysteries that challenge our models of planetary atmospheres. Composition, a chemical nightmare. The atmosphere of Venus is composed primarily of carbon dioxide, which makes up approximately 96.5% of the total atmospheric mass. The remaining 3.5% consists mainly of nitrogen, with trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon. This composition stands in stark contrast to Earth's atmosphere, which is 78% nitrogen and only 0.04% carbon dioxide. The overwhelming dominance of carbon dioxide on Venus creates the most extreme greenhouse effect in our solar system. The clouds of Venus, which completely obscure the surface from optical observation, are not made of water vapor like Earth's clouds. Instead, they consist of tiny droplets of concentrated sulfuric acid suspended in the carbon dioxide atmosphere. These clouds form a continuous layer between 45 and 70 kilometers above the surface, with the densest concentration at around 50 kilometers altitude. The sulfuric acid is highly concentrated, estimated at 75 and 85% concentration, strong enough to dissolve metals and organic compounds instantly. The presence of sulfuric acid clouds raises immediate questions. Where does the sulfur come from? How is the sulfuric acid formed and maintained? Why doesn't it rain out of the clouds and accumulate on the surface? The answers involve complex atmospheric chemistry. The sulfur likely originates from volcanic eruptions on the surface, which release sulfur dioxide into the atmosphere. In the upper atmosphere, ultraviolet radiation from the sun breaks apart sulfur dioxide and carbon dioxide molecules, creating highly reactive chemical species that combine to form sulfuric acid. Below the cloud deck, the atmosphere becomes increasingly hot and dense as you descend toward the surface. The lower atmosphere contains very little sulfuric acid. Any droplets that fall from the clouds evaporate long before reaching the surface due to the extreme heat. Instead, the lower atmosphere is dominated by carbon dioxide gas at crushing pressure. At the surface, the atmospheric pressure is 92 bar, equivalent to the pressure found at a depth of 900 meters in Earth's oceans. This pressure is sufficient to crush most spacecraft and makes surface exploration extremely challenging. Water vapor is present in the Venusian atmosphere, but only in tiny trace amounts, about 20 parts per million, roughly 100,000 times less than Earth's atmosphere. This extreme dryness is one of Venus's greatest mysteries. Venus should have started with approximately the same amount of water as Earth, based on planetary formation models. Where did all the water go? The answer to this question is crucial for understanding Venus's evolution and has profound implications for planetary habitability. The atmosphere also contains mysterious trace chemicals that hint at ongoing geological or even potentially biological activity. Phosphine, a gas that on Earth is produced primarily by biological processes or industrial activity, was controversially detected in Venus's clouds in 2020, sparking intense scientific debate about its origin and whether it might indicate microbial life. Subsequent analyses have questioned this detection, but the possibility of unexpected chemistry or even exotic life in Venus's clouds continues to fascinate scientists. The greenhouse effect, runaway catastrophe. The extreme heat of Venus is not caused by its proximity to the Sun, but by the most intense greenhouse effect known in our solar system. The greenhouse effect is a natural phenomenon where certain gases in an atmosphere trap infrared radiation, warming the planet's surface. On Earth, this effect keeps our planet warm enough for liquid water and life. On Venus, the same process has run away to create surface conditions that would sterilize and destroy any spacecraft within hours. Here's how Venus's greenhouse effect works. Sunlight penetrates through the upper atmosphere and cloud layers, with about 2% of incoming solar radiation reaching the surface. This energy warms the surface, which then radiates heat as infrared radiation. However, the thick carbon dioxide atmosphere is extremely opaque to infrared radiation. It effectively traps this heat, preventing it from escaping to space. The heat accumulates, driving surface temperatures to extreme levels. The sulfuric acid clouds contribute to the greenhouse effect by reflecting about 75% of incoming sunlight back into space, making Venus the most reflective planet in our solar system. This might seem like it would cool the planet, but the clouds also trap infrared radiation from below, contributing to the warming. The result is a delicate balance where Venus absorbs relatively little solar energy but retains virtually all the heat that reaches its surface. The temperatures on Venus are remarkably uniform. Unlike Earth, where temperatures vary dramatically between day and night, equator and poles, summer and winter, Venus maintains a nearly constant temperature of 465 C across its entire surface. The dense atmosphere efficiently transports heat around the planet, eliminating temperature differences. This uniformity is both fascinating and terrifying. There is no escape from the heat anywhere on Venus's surface. Scientists believe Venus experienced a runaway greenhouse effect early in its history. Initially, Venus may have had oceans of liquid water like Earth. However, as the young sun brightened and warmed, more water evaporated into the atmosphere. Water vapor is itself a greenhouse gas, so this increased the greenhouse warming, which caused more water to evaporate, creating a positive feedback loop. Eventually, the oceans completely evaporated, and the water vapor was broken apart by ultraviolet radiation in the upper atmosphere. The hydrogen escaped to space, while the oxygen combined with rocks on the surface. This left Venus with a dry, carbon dioxide-dominated atmosphere. The runaway greenhouse on Venus has sobering implications for Earth. While Earth's atmosphere contains far less carbon dioxide than Venus, human activities are increasing atmospheric CO2 concentrations at unprecedented rates. Could Earth experience a runaway greenhouse effect like Venus? Most scientists believe Earth is not at immediate risk of becoming Venus-like, partly because Earth is farther from the Sun and receives less solar energy. However, understanding the mechanisms that drove Venus's climate catastrophe helps us better understand the limits of Earth's climate stability and the long-term consequences of greenhouse gas emissions. Atmospheric structure. Layers of hell. The atmosphere of Venus is stratified into distinct layers, each with unique characteristics and mysteries. Understanding this vertical structure is crucial for interpreting Venus's climate and dynamics. Unlike Earth, where we live at the bottom of the atmosphere under relatively benign conditions, Venus's surface represents the most extreme and hostile environment, with conditions moderating as you ascend through the atmosphere. The lowest layer, from the surface to about 50 kilometers altitude, is the troposphere, an inferno of dense hot carbon dioxide. Temperatures at the surface reach 465 C, hot enough to melt lead, tin, and zinc. The atmosphere here is so dense that it behaves almost like a fluid, and the visibility would be only a few kilometers even if you could survive the conditions. Soviet Venera landers that reached the surface in the 1970s and 1980s transmitted data for only a few minutes to hours before succumbing to the extreme heat and pressure. The lower troposphere is clear of clouds but hazy with suspended dust and chemical aerosols. Between 45 and 70 kilometers altitude lies the cloud deck, three distinct layers of sulfuric acid clouds that completely enshroud the planet. The upper cloud layer, from 57 to 70 kilometers, consists of small haze particles. The middle cloud layer, from 52 to 57 kilometers, is the densest and most opaque, containing the highest concentration of sulfuric acid droplets. The lower cloud layer, from 45 to 52 kilometers, is less dense. These clouds permanently hide Venus's surface from view at optical wavelengths, which is why radar must be used to map the Venusian surface. Interestingly, within the cloud layer at about 50 to 60 kilometers altitude, conditions are surprisingly Earth-like. The temperature ranges from 0 C to 50 C, and the atmospheric pressure is similar to Earth's surface pressure. This habitable zone in Venus's atmosphere has led some scientists to speculate about the possibility of microbial life existing in the clouds, floating in the droplets of sulfuric acid. While this seems unlikely, extremophile microorganisms on Earth have shown the ability to survive in concentrated sulfuric acid, suggesting that life in Venus's clouds, while exotic, is not completely impossible. Above the clouds, from 70 to 95 kilometers, lies the mesosphere, where temperatures decrease with altitude. The sulfuric acid droplets that form the clouds evaporate in this region due to heating by absorbed ultraviolet radiation, releasing sulfur dioxide and water vapor back into the gas phase. This region sees complex photochemistry driven by solar ultraviolet radiation, creating a variety of reactive chemical species. The thermosphere extends from 95 to about 200 kilometers altitude. Here, temperatures rise again due to absorption of solar, ultraviolet, and X-ray radiation. The atmosphere becomes increasingly tenuous at these altitudes, and the composition begins to change as lighter gases separate from heavier ones. Above 200 kilometers is the exosphere, where the atmosphere gradually transitions to the vacuum of space. The exosphere is where Venus loses atmospheric gases to space, including any remaining water vapor, a process that has been ongoing for billions of years. Superrotation, the fastest winds in the solar system. One of Venus's most baffling mysteries is the superrotation of its atmosphere. While Venus rotates on its axis once every 243 Earth days, the atmosphere at cloud level races around the planet in only 4 Earth days, a speed about 60 times faster than the planet's rotation. This means wind speeds in the cloud layer reach 350 kilometers per hour or more. making Venus's winds among the fastest in the solar system, despite the planet's sluggish rotation. This superrotation is completely unexpected based on simple atmospheric physics. On Earth, the atmosphere rotates at roughly the same speed as the planet's surface, because friction and other force couple the atmosphere to the solid planet below. On Venus, somehow the atmosphere has become almost completely decoupled from the surface, spinning around the planet at tremendous speeds, while the surface barely rotates at all. The superrotation is not uniform with altitude. At the surface, wind speeds are relatively gentle, only about 1 meter per second. As you ascend through the lower atmosphere, wind speeds gradually increase. The fastest winds occur in the cloud layer at around 60 kilometers altitude, where they reach their peak of 350 km/h or more. Above the clouds, in the mesosphere and thermosphere, wind speeds decrease again. This vertical wind profile adds to the puzzle. What maintains this structure? Why are the fastest winds at cloud level rather than higher or lower? The superrotation also varies with latitude. The fastest winds are found at mid-latitudes between 30 and 50 degrees north and south of the equator. Near the equator, winds are somewhat slower, and at the poles, they form strange vortex structures, dynamic, swirling cloud patterns that constantly evolve and change shape. These polar vortices are visible in ultraviolet images of Venus, appearing as dark regions at each pole with complex, irregular structures that rotate around the pole every 2 to 3 days. Scientists have proposed various mechanisms to explain superrotation, but no single theory fully accounts for all observations. One leading hypothesis involves thermal tides, atmospheric waves generated by solar heating that can transfer angular momentum from the planet to the atmosphere. As the Sun heats Venus's thick atmosphere, it creates pressure waves that propagate around the planet. These waves can interact with the planet's slow rotation in ways that accelerate the atmosphere, gradually spinning it up to superrotation speeds. Another factor may be the vertical transport of momentum by atmospheric waves and turbulence. Convection in the lower atmosphere and wave motions in the upper atmosphere can transport momentum vertically and horizontally, potentially maintaining the superrotation against friction with the surface. Computer models attempting to simulate Venus's atmosphere must include these complex processes to reproduce the observed superrotation, but even the most sophisticated models struggle to fully capture the dynamics. The superrotation has practical implications for Venus exploration. Any probe entering Venus's atmosphere will be swept rapidly around the planet by these intense winds, making it difficult to study specific surface locations for extended periods. Balloons or aircraft designed to float in Venus's upper atmosphere would circle the planet in just 4 days, experiencing a wide range of conditions but unable to remain stationary over any given location. Understanding Venus's superrotation is not just an academic exercise. The same atmospheric physics that produces superrotation on Venus may be relevant to understanding atmospheric circulation on other planets, including hot Jupiters, giant planets orbiting very close to their stars, and Earth-like exoplanets. Venus serves as a laboratory for studying atmospheric dynamics under extreme conditions, potentially revealing universal principles of planetary atmospheres. Chemical mysteries and active processes. Beyond the well-known components of carbon dioxide and sulfuric acid, Venus's atmosphere contains chemical mysteries that hint at active processes and potentially even ongoing volcanic activity. The atmospheric chemistry of Venus is far from equilibrium, meaning chemical reactions are continuously producing and consuming various compounds, maintaining the atmosphere in a dynamic state. One key mystery involves the sulfur cycle. Observations show that the amount of sulfur dioxide in Venus's upper atmosphere varies significantly over time, sometimes changing by factors of 2 or more over the course of years or decades. This variability is puzzling because sulfur dioxide should be relatively stable on these timescales based on known chemical reactions. The most likely explanation is episodic volcanic activity, with eruptions injecting large quantities of sulfur dioxide into the atmosphere, followed by gradual chemical conversion to sulfuric acid and eventual removal. Evidence for active volcanism on Venus remains circumstantial but suggestive. The surface shows thousands of volcanic features, and the relatively young age of the surface, lacking the heavy cratering expected for an ancient, inactive surface, suggests recent geological activity. Some studies have reported transient hotspots on the surface that might indicate active lava flows. However, definitive proof of current volcanic activity remains elusive, partly because Venus's dense clouds prevent direct optical observation of the surface. The presence of carbonyl sulfide in Venus's atmosphere also puzzles scientists. This compound forms through reactions involving carbon dioxide and sulfur compounds, but its abundance is higher than expected from known chemistry. Understanding the full sulfur chemistry of Venus requires accounting for dozens of interconnected chemical reactions occurring at different altitudes and temperatures, many of which are poorly understood under Venus-like conditions. Another chemical mystery involves the atmosphere's oxidation state. Despite the presence of sulfuric acid, a strong oxidizer, Venus's lower atmosphere shows evidence of being relatively reducing, having little free oxygen. This creates a chemical disequilibrium that must be maintained by ongoing processes, possibly involving reactions with volcanic gases or surface minerals. The controversial detection of phosphine in Venus's clouds in 2020 sparked intense scientific debate and media attention. Phosphine is a simple molecule consisting of one phosphorus atom and 3 hydrogen atoms. On Earth, it is produced primarily by anaerobic bacteria or industrial processes. There are no known abiotic, non-biological processes that produce significant amounts of phosphine in Earth-like conditions. The reported detection of phosphine in Venus's clouds raised the tantalizing possibility of microbial life floating in the Venusian atmosphere. However, the phosphine detection has been strongly challenged. Reanalysis of the original data suggested that the signal attributed to phosphine might actually be sulfur dioxide or simply noise in the measurements. Subsequent observations have not conclusively confirmed the presence of phosphine, though they also have not definitively ruled it out. The debate highlights both the excitement surrounding potential biosignatures and the difficulty of detecting trace gases in Venus's complex atmosphere. Whether or not phosphine exists in Venus's clouds, the episode has reinvigorated interest in Venus's atmospheric chemistry and the possibility of life in the clouds. If microbial life does exist in Venus's atmosphere, it would represent a completely different biochemistry from terrestrial life, capable of surviving in concentrated sulfuric acid at moderate temperatures. Some scientists have proposed that such life might have originated on Venus's surface billions of years ago when the planet may have had liquid water oceans, then adapted to living in the atmosphere as the surface became uninhabitable. The lost water, Venus's great drying. Perhaps the most profound mystery of Venus's atmosphere concerns what happened to the planet's water. Based on similarities in size, composition, and distance from the Sun, Venus should have formed with approximately the same amount of water as Earth. Yet today, Venus's atmosphere contains roughly 100,000 times less water than Earth's. Where did all this water go? The leading theory suggests that Venus lost its water through a multi-stage process, beginning early in the planet's history. Initially, Venus may have had oceans of liquid water similar to Earth's. However, being closer to the Sun, Venus received more solar radiation, and as the young Sun gradually brightened over its first billion years, Venus's surface temperature increased. This caused more water to evaporate into the atmosphere. Water vapor is a potent greenhouse gas, so increased atmospheric water vapor enhanced the greenhouse effect, raising temperatures further and causing even more water to evaporate. This positive feedback created a runaway greenhouse effect, where the oceans completely evaporated into the atmosphere. At this point, Venus would have had a thick water vapor-rich atmosphere with surface temperatures potentially exceeding 1000 C. In the upper atmosphere, solar ultraviolet radiation photodissociated water molecules, breaking them apart into hydrogen and oxygen. The light hydrogen atoms, having high thermal velocities, escape to space more easily than heavier gases. This process, called hydrodynamic escape, was very efficient for the hot, water-rich early Venusian atmosphere. Over millions of years, Venus lost essentially all of its hydrogen and thus its water to space. The oxygen released by water photodissociation did not escape as easily. Instead, it reacted with rocks on the surface and with volcanic gases, becoming incorporated into surface minerals. This oxidation of the surface may explain why Venus's surface appears more oxidized than Earth's mantle, despite the reducing conditions in the current atmosphere. Some water remains on Venus, but only in tiny amounts. The ratio of deuterium, heavy hydrogen, to normal hydrogen in Venus's remaining water is about 120 times higher than on Earth. This isotopic enrichment supports the escape scenario. Normal hydrogen escapes to space more easily than deuterium, so over billions of years of hydrogen loss, the deuterium becomes concentrated in the remaining water. Understanding Venus's water loss has important implications for planetary habitability and the search for life elsewhere in the universe. It demonstrates that being in the habitable zone, the region around a star where temperatures allow liquid water, is not sufficient for maintaining habitable conditions. A planet must also regulate its greenhouse effect and avoid runaway processes that can lead to water loss. Venus may have been habitable for hundreds of millions or even billions of years in its early history, before crossing a threshold beyond which the runaway greenhouse became inevitable. Recent research suggests that plate tectonics, or rather, the lack thereof, may have contributed to Venus's fate. Earth's plate tectonics plays a crucial role in regulating atmospheric carbon dioxide through the carbonate-silicate cycle. Rainfall weathers rocks, dissolving carbon dioxide from the atmosphere. Rivers carry dissolved minerals to the oceans, where they precipitate as carbonates. Subduction then carries these carbonates into the mantle, where they are eventually released through volcanism, completing the cycle. This process acts as a thermostat, stabilizing Earth's climate over geological timescales. Venus lacks plate tectonics, possibly because the loss of water early in its history affected the composition and viscosity of its mantle, preventing the development of mobile tectonic plates. Without plate tectonics, Venus could not regulate its atmospheric carbon dioxide through the carbonate-silicate cycle. Volcanic outgassing continuously added carbon dioxide to the atmosphere, but no mechanism removed it, allowing the greenhouse effect to strengthen over time. This created another positive feedback. Greenhouse warming prevented water from being removed from the atmosphere into surface reservoirs, maintaining the conditions for continued water loss. Exploring the toxic atmosphere. Missions to Venus. Despite its extreme conditions, Venus has been visited by dozens of spacecraft since the early space age, providing our knowledge of this enigmatic world. The Soviet Union's Venera program achieved remarkable successes, including the first soft landing on another planet, Venera 7 in 1970, and the first images from the surface of another planet, Venera 9 in 1975. These achievements required extraordinary engineering to create spacecraft that could survive Venus's crushing pressure and searing heat, even if only for minutes or hours. The Soviet Venera landers revealed a desolate rocky surface, illuminated by the dim orange glow that penetrates the dense atmosphere. The rocks appeared volcanic in origin, and chemical analyses confirmed basaltic compositions similar to volcanic rocks on Earth. The spacecraft measured temperatures of 462 C and pressures of 89 bar at the surface. Wind speeds were surprisingly gentle, about 1 meter per second, despite the fierce winds higher in the atmosphere. The Venera missions lasted between 23 minutes and 127 minutes before failing due to the extreme conditions. NASA's Pioneer Venus mission, which arrived in 1978, consisted of an orbiter and a multi-probe entry package. The orbiter operated for 14 years, mapping Venus's gravity field, monitoring atmospheric composition and dynamics, and studying the interaction between Venus's atmosphere and the solar wind. The entry probes measured atmospheric structure, composition, and cloud properties at different latitudes, providing the first detailed vertical profiles of Venus's atmosphere. The Magellan spacecraft, which orbited Venus from 1990 to 1994, used radar to map Venus's surface at high resolution, revealing the volcanic landscape in exquisite detail. These maps showed that Venus had been geologically active relatively recently, but raised questions about why the planet lacks plate tectonics and how its volcanic activity compares to Earth's. The European Space Agency's Venus Express, which orbited from 2006 to 2014, studied atmospheric dynamics, composition, and the interaction with the solar wind. It discovered features suggesting ongoing volcanic activity and provided detailed observations of the polar vortices and superrotation. Japan's Akatsuki orbiter, which began operations in 2015 after a 5-year orbital insertion failure, continues to study Venus's atmospheric dynamics, weather patterns, and cloud structure at multiple wavelengths.